Hello students, this video is designed to help you review for the final exam in elementary statistics. You're going to be taking that exam shortly, so make sure that you try these questions first. It was the final exam review that was posted on the website, and as soon as you are done with them, you come back here and check your answers. Don't watch this video before trying the questions, because then you'll have no idea whether you understand it or not. Alright, hopefully you started that page. We're starting at question number 11. Pause the video if you didn't, try it out, and then see if you got them right. Alright, in this first problem, it gives us a situation where 500 children are asked whether they read books for fun every day. Obviously, everybody probably said yes. No, that's not the case. This is a two-way table. A two-way table summarizes information on multiple different categories of variables, whether students were boys or girls, whether students said yes or no, and then their totals. Sometimes you'll get the totals filled out, sometimes you won't, but the totals are pretty easy to find. For example, 48 plus 76 is equal to 124. That's a row total. 76 plus 194 is 270. That's a column total. You can test the other numbers yourself. And one other thing to notice, 124, 376, when you add them together, that gives you 500. And then 230 and 270, that also gives you 500. That's how a two-way table works. The first question asks us the proportion of children in the survey who are boys. We added the boys together, that's 230, and divided that by 500, which is the total. That's 0.46. What proportion of boys in the survey read books for fun every day? Well, it's the proportion of boys. So your denominator now is going to be only boys. This is an example of conditional probability. The total number of boys is 230. The ones in there that read books is only 48. We're not using this number because this number is made up of boys who read books, but also girls who read books. So we're not using the 124, we're using 48. So 48 out of 230 is 0.209. What proportion of girls in the survey read books for fun every day? Same thing we did from before. It's asking for a proportion of girls. So we're only looking at the girl total. That's 270. So 76 divided by 270, that should be 0.281. That was summarized over there. Do the results of the survey suggest that gender has an effect on reading books for fun? There is a test that you can do for this, but it's a test that's beyond the scope of this course. All we can say is that we can surmise that there is an effect there. We don't know how significant the effect is, but they're pretty different. The percentages are off by, 7 percentage points. 0.21, that's about 21%. 0.28, that's about 28%. Are these two events independent? A child reads books for fun every day, and a child is a boy. Are they independent? Well, independence test is this. Probability of A times probability of B is equal to the probability of A and B. This is the probability independence test that you will always use to determine whether two events are independent. Well, we're looking at two different events. Let A be reading books for fun and B be a boy. The probability of A we didn't find out before, but the probability of A is easy to figure out. The folks that read books for fun, that's 124 over 500. Those are all the yeses. The probability of being a boy is 230 over 500. We did find that before. The 230 number on the two-way table, that's 0.46. And when we multiply those two numbers together, we get 0.11408. On the two-way table, we're able to see that the probability of A and B, which is reading books for fun and being a boy, that's 48 over 500, that's 0.096. These two numbers are not the same. If the events were independent, then this number, 0.096, and this number, 0.11408, would be the same. But they're not, so they're not independent. It's as easy as that. For question number 12, it asks us a situation where we're picking walls out of a bin, and it says without replacement. As soon as it says without replacement, we know that we are not doing independent events. Because think about it. You have 7 balls in this bin. When you pick one out and you don't put it back, there are only 6 balls left. So that means we've changed our probabilities. So if the probability changes, we can say it is not a binomial random variable. Made a tree diagram down here, and the tree diagram has all the probabilities with all of the colors. The first pick is either red or green. And then based on that first pick, let's say I pick a red one here, there were 3 reds in the container and 7 total. Well, now I've picked a red already, so now there's only 2 reds left, and there's 6 balls total. If I were to pick a green first, however, 4 out of 7, now there's only 3 greens and 6 balls. There's still 3 reds. So the difference between this branch and this branch is that, well, we've picked a red out first here on this path, and we haven't picked a red out here on this path. Incidentally, this arrangement is called the sample space, all the possible outcomes. On test number 2, I asked you to write out a sample space of, I think it was flipping coins or rolling dice, but it's just writing out all the different possible outcomes. We found out the probabilities by multiplying the branches. Of course, with multiple events, you multiply. That's how this works. And then we figured out the probability table based on that. X is the number of green balls chosen. So X equals 0. Well, that's only the probability of first getting a red ball and then getting a red ball. That's 1 out of 7. In order to get one green ball, you could either do red and green, which is 2 out of 7, or you could do green and red, which is also 2 out of 7. So these two outcomes, I guess they are probabilities also, added together is 4 out of 7. And then the probability of getting 2 greens is 2 out of 7. Well, X equals 2 means the number of green balls, and that's what it said in the problem. It said the random variable is the number of green balls chosen. For question 13, it asks why it's a binomial random variable. There are certain criteria that it has to meet for it to be a binomial random variable. If you have a set number of trials, if you have a binary outcomes for every trial, if they're independent, and a fixed probability of success. So the explanation is there. A probability distribution table for X is very easy to do because all we're doing is using our calculator to do so. Instead of making a tree diagram, which would be very exhaustive, we use binomial probability distribution function. In this case, it's binomial, so we're able to say the number of trials is 3. The probability of success is 4 out of 7, and the number of successes is that last number. In the first case, we're doing 0. That's where this 0.087 came from. We plugged it into the calculator. We did the same thing for probability of 1 success. The only thing we did was 3, 4/7, and then 1, and we got 0.3149. A good way to check to see if this probability distribution is accurate is to add these numbers together. Guess what? They should equal 0. Finding the mean is of any binomial probability distribution is mu is equal to n times p, the number of trials, times the probability of success. So 3 trials, success probability 4/7, that's 1.714. And then the law of large numbers states that as more and more trials are performed, the average results will approach the mean. So the law of large numbers says, well, you might win in a very small amount of cases. You might have an abnormal amount of wins, or you might have an abnormal amount of losses. But if you do it 1,000 times or 1,000,000 times or 1,000,000,000 times, we expect your results to look a lot like the mean. So as we repeat the experiment many times, law of large numbers, you're looking for the words repeating the experiment many times. We expect the average green ball count to be 1.714. All right, moving on to question number 14. It talked about a dice rolling game. The dice rolling game was simple. If you roll an odd number, you win that amount of money, so $1, $3, and $5. If you roll an even number, you lose that amount of money, so -2, -4, -6. This is your probability distribution table. Your profit, if the outcome of the roll is 3, you win $3 because it says you win as many dollars as you rolled if it's odd. For letter C, the expected value is all the probabilities times all the payouts. So we did 1 times 1/6 times -2 times 1/6, because remember, you're not winning this $2, you're losing it. 3 times 1/6, -4 times 1/6, etc. That's 0.5. You can do that very easily on your calculator. Expected value is the average result. So upon many repeated games, again, that repeated games idea, this is the law of large numbers in a different way. The average result is -0.50. That's 50 cents lost. And if you're talking about, if you play the game where you do the experiments a set number of times, how much would you expect to win or lose? It's very easy. Take that number 100 times and multiply it by the expected value of X, which is the average winning or losing. So 100 times -0.5, -50. So you lose $50. Question number 15. You're paying $2 to play a game of chance. This is going to come in really important soon. It says you're paid $10 if your coin shows a tail. So you say to yourself, oh, I win $10. Well, not really, because you paid $2 to play the game. So the payout isn't $10. It's 10 minus 2, which is $8. Again, you paid $2 to play the game. You lost that money regardless. You're only given back $10 if you win. So the winning probability is 1 out of 6. Because tails in 5 out of 6 is 1/2 for the tails, 2 out of 6 for a 5 or a 6. That probability is 2/12 or 1/6. And when you lose $2 because you lose your pay-in or your buy-in. Your expected profit is very easy. It's the same expected values from before, and your expected loss is 33 cents per game. So that's -0.33. This is supposed to say lose, not loose. Sorry about that. If you play the game 100 times, I'm not going to review that again because, well, frankly, I just talked about it. Looks like I got a little bit cut off here, so I'm going to slide it a little. A binomial random variable has 4 different qualities. A binary result, either defective or working. Independent, one probability doesn't affect the others. The number of trials is set. In this case, it's 10 TVs, and the success probability is 0.02. In this case, success is defined as whether the TV is defective. A weird way to define success, to be sure, but it's not talking about, oh yes, we want success. It's talking about we're getting the result that we're looking for. The number of trials here is 10 because in every sample, in every shipment, we're looking at 10 TVs. A success is if a TV is defective. Again, that's a little counterintuitive, but that's what we're looking for. One defective TV isn't going to affect the others. It's not like one defective TV is going to infect other TVs. I hope, because that would be terrifying. And then the value of P, which is the success probability, is 0.02. It says 2% of the television sets are defective. So that's a known probability. That's a known proportion for the population. The probability that the shipment is accepted, it's an easy thing to figure out if you're using your calculator. You can say binomial cumulative distribution function, binomial CDF. It's talking about all of the values of that number and below. So the probability of 1 and all the numbers below it. In this case, it's the probability of 1 and the probability of 0. So binomial CDF 10, 0.02, and then 1 gives me 0.9838. That's the probability of getting 1 TV or less. So it's a pretty high probability that the shipment is accepted. Think about it. It's a 0.02% chance for every TV being defective. It's pretty low that 2 or more TVs are defective. And then the expected value, same exact formula from before. And then we're filling in the information, random samples of size 10. Well, we learned about that from before. That's the number of trials. And then 0.2 is the average number of defective television sets because that's our mean. That's our expected value. Moving right along to question number 17. A test has 10 true-false questions. The probability of getting a true-false question is 0.5. That should make perfect sense to you. 10 trials. 8 successes. That's what we're looking for. At least 8. So either 8, 9, or 10. The probability that the student will pass the test, I could do the probability of 8 plus the probability of 9 plus the probability of 10, but I'd rather not. I'd rather use my calculator. So I need to use my calculator, but I can only do less than or equal to, as was described in the previous question. So I can't put x is greater than or equal to 8 in my calculator, but I can use binomial CDF with x is less than or equal to 7. Here's an example of what it looks like in the calculator. Now, if you're wondering why I'm using 7 here and not 8, think about it. I'm looking for the probability that x is greater than or equal to 8. The calculator does less than or equal to only, so I can't put 8 in there because this says we want the probability of 8 in our answer. So I'm looking for the probability of 7 or less. Because if I'm looking for the probability of 7 or less, those are all the situations in which we would fail the test. It asks for the mean and standard deviation. This is boring old hat stuff. You have the formula for these two things. And then is it unusual for a student to pass by guessing? No, because unusual means 0.05 or less, and 0.055 is greater than that. So that's what we talk about when we say unusual. In this last question in this section, question 18, it's not binomial because we're talking about without replacement. And without replacement means the events are not independent. But we can still figure it out by multiplying the two events. 14 out of 40 times 13 out of 39. I got 14 because I know that 35% of 40 is equal to 14 people, and it says 35% of this group of 40 have never been abroad. And once I pick the first person that's never been abroad, my new total number for people who have never been abroad goes down, so does my total number of people. And then the probability that at least one has been abroad, it's the same as saying 1 minus the probability that no one's been abroad. I'm using the complement rule here. All right, moving on to questions 19 and 20. These are the normal distribution. I'll come back for the rest of these questions in the third video. It's a bell-shaped distribution, a normal curve. It gives us the mean and standard deviation. Those go inside the normal CDF formula in the calculator. The first argument is lower bound. Next is upper bound. Next is the mean. And next is standard deviation. Plug that into the calculator. You're good to go. We're doing the same kind of calculation here. X is greater than 72. That means 72 is my lower bound. My upper bound is 10 to the 99th. Here we're doing a calculation where we're looking between two values. And here we're given area under the curve, so we have to use the inverse. It's called inv norm. All right, that is the video that describes how to do the next 10 questions from the final exam review. Check back again for the third video, and good luck studying.